Okay, so we're working on some material here out of Box C of Unit 910, and we want to start talking about what we mean when we talk about derivatives. What is a derivative? What do they represent? And at this point right now, let's just say that what derivatives are, they're a way of greatly simplifying this process of finding tangents. So I'll just say here that it simplifies the process of finding tangents. Because that's what we've been working on for the past couple of days here, is looking at slopes of tangents and equations of tangents and things like that. So first off, just a definition here. The derivative of a function, we've got some function f at x, at a particular point, where the coordinates of this point are a, f at a, where a is just some number here. The derivative represents, there are kind of two ways of thinking about what the derivative represents. One of them is that it represents the slope of the tangent to the curve, which is the curve which is of course given by the function f at x, okay, at that point P. So if we go to point P, we draw the tangent. The derivative tells you the slope of that tangent at that particular point. The other way of interpreting derivatives is that they represent the instantaneous rate of change. Instantaneous rate of change of this function, okay, so of the function f at x, and it's changing. What is it changing with respect to? Well, it's changing with respect to x. Again, at point P. And we're going to look at two things here today. Okay? We're going to look at how to find, number one, the value of the derivative of a function at a particular point. Okay? And then we're going to look at how you do something that is a little bit more useful, how we find what's called the derivative function. Now, the derivative function is represented by f, the little prime symbol there, at, and then x. So it's a function. We call it f primed at x. And this function, the derivative function, gives us the derivative of our original function, f at x, for any value of x that we put in there. So we're going to look at doing it for a specific point, x equals a, and then we're going to look at doing this a little bit more generally. So the result of 2 here will be a function which will give us the derivative at any point, or the slope of the tangent at any point. Okay? Sound good? All right. Okay, so here's where we're going to start. We're going to find the derivative at a particular point A that we know. So let's say we've got some function, and I'll just do a nice little smooth function like this. We'll call this function f at x, because that's a good name for a function. And let's say we are interested in a point right here, an x value that is a. I mean, a can be any number we want. I'll label these axes x and y. And what we want to do is we want to find the slope of the tangent at that point A. Or this point here is going to have coordinates. My x is A, and my y is f at A. Okay, so I can just evaluate the function at A to get the y coordinate. Now, from what we talked about yesterday, the way that we were figuring out the slopes of tangents was we went to another point that was away from the point that we were interested in, okay, and we constructed a secant between these two lines. Okay. So let's say we went, the second point here is some distance away from A. And let's call this distance h. Okay, so that's the separation between these, the separation in x, or the difference in x between these 2 points that I've drawn here. So if this one here is A, and I'm going h further along, this one is going to be A plus h. That means the coordinates of this point are A plus h is my x value, and to get my y value, I just evaluate the function at A plus h. So coordinates are A plus h, f at A plus h. And the big thing we did in the last lesson was we said, okay, to get the slope of the tangent, we took this point and we imagined moving it closer to the point at A. So essentially what we're doing here is we're taking this separation h and we're making it very, very smaller. So we're letting h go to 0. And as we let h go to 0, as we move that second point on our secant closer and closer to our original point, our secant becomes closer and closer to a tangent, which is what we're interested in. And we're always interested in the slope of all of this stuff. So if what we're calculating is the slope of the secant that we've drawn there, well, the slope of the secant is delta y over delta x. And if we do our delta y here, let's see, our second y value is right here, f at A plus h. Okay. And our first y value is f at A. Our second x value is just A plus h. And we want to subtract our first x value, which is just A. And we can simplify this a little bit right off the bat. We can turn this into f at A plus h minus f at A. And then on the bottom, A minus A cancels out, and we're just left with h. And what we want to do is, as we move this second point closer and closer, okay, we're letting h get smaller and smaller and smaller. So what this amounts to is taking the limit as h tends to 0. So the slope of the tangent at point A is going to be the limit as h goes to 0 of this expression that we have right here. F at A plus h minus f at A, all divided by h. I'll just get rid of that dot there. And this right here is the expression that we're going to use to find the slope of the tangent, or the derivative, at a very specific point. Okay? So let's just take a look at an example of how we would use this here. Okay? So let's say we want to find the derivative of the function f at x equals x squared plus 2 at the point x equals negative 3. So we'll start with our formula here, and we'll just say our derivative we're going to represent by f primed at the point negative 3. Okay? So this means derivative at x equals negative 3. And let's just use that definition that we had on the previous slide. So the limit as h goes to 0 of f at A plus h minus f at A, all divided by h. And we know what our function is. So We've got to keep this limit stuff here. Our function is x squared plus 2. So in the numerator, we're going to evaluate this function at a plus h. So a is negative 3, so we've got to evaluate, I'll just put this step in, 3 plus h minus f at negative 3, all divided by h. And let's put in the information that we know about our function. So we want to evaluate x squared plus 2 at negative 3 plus h. So that's going to be negative 3 plus h squared, just subbing in negative 3 plus h wherever I see that x, plus 2 is sort of our first term there. And we want to subtract from that x squared evaluated at, x squared plus 2 evaluated at negative 3. So just put in what I know my function to be. And on the bottom, I still have that h there. Now, eventually what I want to do is I want to get to a point where I can sub h equals 0 into this expression that I have here. I can't do that yet because I've got this h on the bottom, and if I sub in 0, I'll be dividing by 0, and that's no good. So I need to keep simplifying what I have up at the top. So the first thing I'm going to do is I'm going to expand this first expression here. So I've got negative 3 plus h. I'm going to square it, so I'm going to expand that. And I'm going to get, what am I going to get here? 9 minus 6h plus h squared plus 2 is my first expression there. And I'm going to subtract, let's see, what do I have in there? I have negative 9 squared, negative 3 squared is 9. 9 plus 2 is just 11. Still, all divided by h. Well, let's simplify this a little bit more. I can subtract, let's see, I got 9 plus 2 in here, which is 11. And then I subtract 11. So that's going to, all those number terms are going to cancel out. And I'll be left with negative 6h plus h squared all over h. Now, why is this good that I've gotten to this point here? Nick? Yeah, I can cancel out an h on the top and bottom. And I'll just, it's clear that I can do that, but I'm just going to toss in a little step here where I factor out the h on the top. So this is h times negative 6 plus h all divided by h. And then we can cancel out those two h's. So now I have the limit as h goes to 0 of negative 6 plus h. Which is good because now that I've gotten rid of that h down in the denominator, I can evaluate this limit by subbing in h equals 0. So I'll just say sub in h equals 0 at this bottom step. My limit is gone. I get negative 6 plus 0, and which is just negative 6. So the value of my derivative at that point, x equals negative 3, is negative 6. So that negative 6 would represent the slope of the tangent to the curve f at x equals x squared plus 2. At that point, x equals negative 3. So the next thing we want to look for is we want to look for how we can find the function that represents the derivative at any point that we're interested in here. And the process is very, very similar, okay? It's essentially, it's the same formula, except instead of having that specific value of a in there, we're just going to have the general expression, we're just going to have x in there instead. So we can have, again, our derivative at any value of x, or f primed at any x, is going to be the limit as h goes to 0 of our function evaluated at instead of a plus h, or that specific value plus h, now just in general at x plus h minus our original function evaluated at x, all divided by h. Okay? And this thing right here is sort of the big definition that comes out of parts A, B, and C, or boxes A, B, and C. Okay, so this is sort of the definition that we're going to be using for what a derivative is. Okay? And I should say, for all x for which the limit exists. Yeah, I tend to omit things like that because I was trained as a physicist, and we just naturally assume that if the limit doesn't exist, we're not interested in it, so why bother saying things like that? Math people get kind of fussy about saying, you know, things mathematically properly. So this is our derivative function here, okay? And there's a couple of different notations here. F primed at x is very common. Often you'll see something that is dy dx, okay? You'll also see, instead of f primed, you'll see y primed, okay? All of these things just sort of mean the exact same thing. So if you were asked to use this thing to find a derivative function, or the function that represents the derivative of some other function, the question will be phrased something like this. Are we ready to go here? Good? You will be asked to determine f primed at x from first principles. And when you see from first principles, that is the mathematical way of saying they want you to use this definition. The limit as h tends to 0 of f at x plus h minus f at x all divided by h. Okay, so let's look at how we would do this here. We don't have a specific value of x that we can sub in, so we're just going to have to work with the definition of our function here. So we're going to have the limit as h goes to 0. And first off, we want to evaluate this function at x plus h. So everywhere that I have an x in that, I'm going to put x plus h. So this is going to be x plus h squared minus 3 times x plus h. That's my first term. And then from this, I want to subtract my function f at x. So I'm going to subtract x squared minus 3x. On the bottom, I've just got my h there. My next step then is all of this stuff here in the first term, I'm going to want to expand. So we'll have the limit as h goes to 0 of, let's start expanding here. X plus h squared is going to be x squared plus 2xh plus h squared minus 3 times x gives me 3x minus 3h. Remember this negative here applies to both of these terms. And same thing over here. I want to apply this negative sign here and here as well. So this will be minus x squared plus 3x. And if you've done this expansion correctly, at this step here, a whole bunch of things should start canceling out. So I've got an x squared here. I've got a minus x squared here. I've got a minus 3x right here. I got a plus 3x right there. And what I'm left with after doing that canceling is I still have my limit as x goes to 0, as h goes to 0 of 2xh plus h squared minus 3h, all divided by h. And this is good because now all the terms in my numerator have an h in them. So I can cancel out these h's, top and bottom. So this 3h will just become negative 3. H squared will just become h, and h. So I'm going to have the limit as h goes to 0 of 2x plus h minus 3. I can sub in h equals 0 and evaluate my limit and get 2x minus 3. I'll just say over here that I subbed in h equals 0. And I'm done. I don't have a specific value of x that I can put in there. So all this work has told me that f primed at x equals 2x minus 3. Okay? So this is my derivative function, okay? Or the function that tells me the slope of the tangent to my original curve, x squared minus 3x, at any x value that I want. Okay? And if the question gave me a specific value of x, let's say it said at x equals 5, I could find the value of this function at x equals 5 by just subbing that 5 in. So the slope of the tangent at x equals 5 would be 7. So that's how you get the derivative of a function from first principles. Okay? This is the derivative of f at x equals x squared minus 3x, which was my original function. Okay. And that's it for box C.